Okay. So it says we're live. Let me just Are we live? Hello? I think the microphone is probably good. Okay. Tell me if you can't hear me or there is any technical difficulties maybe. How can I bring the chat here window in the wait? There was a way to bring that. I don't know. I'll just do this. Okay, nice. Thanks, Blogway. We have an interesting things for today, and I want your opinion on something. But yeah, so welcome everyone to the stream. Today we're just going to upsolve some problems. We are going to talk about some lemmas maybe, and I want an opinion on something before we start the stream. And I'm not really like sure about legalities and things like that, but I have been, for those who know me quite a bit back, I have been collecting some algorithms and some snippets and from all kinds of sites. And this repository actually that I have here, so you can always go to github.com/mitkonikov/competitive. This repository is filled with solutions, with all my solutions to some problems, and they are divided by categories. They're divided by like where that problem had occurred, or where, what algorithm or what technique this problem uses. So sometimes if a problem if it's an ad hoc problem, I would just put it like in the competition itself. So like AtCoder, let's say. And if a problem uses very specific technique that could be easy to maybe for some new competitor to come here and to say, okay, I want a problem that uses hashing, let's say. And it will see, okay, this grid search from HackerRank uses hashing, and okay, let's go and let's see if you could solve the problem. Okay, solve the problem. If not, you could just take a look at my solution, how I did it, and then see your mistake or something like that. But so my question is, I have one more thing that I have been collecting over the years, and this is not published. This has never been published, and due to the fact that on ACM competitions you could take any book you want or any algorithms you want or anything. So I have been kind of collecting snippets from all over the place, and have this competitive.pdf here, which is like a competitive programming library. it's not been touched since 19th of May, which means I haven't added nothing to the or changed anything since then. You see how busy actually I was these months, but you could this competitive thing here, like I call it competitive programming library, CPL or whatever. It contains all of the common algorithms, things that you might need for competitive programming. Most of the snippets are taken from the KTH library. Some are taken from the EKZ library, if you know these libraries. Some are taken from competitions. Some are my own written, like these, like stable marriage, stable roommate. These I think I wrote, and some like other things. But like, let's say this like minimum cost arborescence. These are really niche techniques, niche things, niche algorithms that no one actually like. I mean, there will be like one problem, one very specific problem that uses this, and I don't think it's useful, but there are a lot of these that I have collected over the years, and I have wrote some even like I have wrote some data structures that are not in here per se, so I haven't added them. But actually, like, there's like mathematic things that I have, like hashing, geometry, miscellaneous stuff. I have some like interesting solutions that I have written over, like I think that might be helpful in some other problems. So technically, I have started to kind of explain some things. So like, let's say topological sort, consistent topological sort, and Euler tour, I have explained this, but let's say this implementation is from the Simon Lindholm library, so it is pretty like small, and I think it's nice. But if you take a look, okay, this isn't even filled up. So if you could see like some implementations, and then you could see this here. So I already have like there are already good implementations of all these things, but yeah, so Blogger says you should definitely give credit where credit is due, but I'm not sure if you have to ask for their permission for that. So the problem is that if you like this, if I distribute these all implementations, even though I can write where they are found and why is this the case, but I think that most of these are like lying around somewhere on the internet, left and right, and it would be really nice to have a open source GitHub repository for this specific like competitive programming algorithms and data structures. So like anyone can add in there, and anyone can contribute, and anyone can test the solutions. But it needs a lot of work. It needs a lot, like adding solutions for all of these things here. For example, explaining how these solutions actually work. Some solutions are not explained. Some solutions have different styles, I would say, because they're taken from different people and different implementations, and like string algorithms. We all know these string algorithms, but I have them separately on like separate books. So this I just use in reality. I have this like printed, and I just use them to find where they are in some other, so like a reference to something, to some other piece of paper. There's like disjoint set unions with undos, with all kinds of things. It's a really I have stolen here some link cut tree from some solution on Code Chef, I think. I don't even, like, I can't even find the author of this here, because this is taken from some solution which then repurposed and changed and a little bit explained maybe some things inside. So it's really difficult. Yeah, inspired is the word, stolen. Yeah. I mean, there are all of these kinds of solutions, and at the end I would really want to have something like this. So something like this where we could kind of have lemmas, so like mathematical lemmas, so like just one piece of mathematics that is true and that you don't have to prove it, and like the proofs could like be referenced to some book or something, or maybe like you could just prove it here, but the proofs actually need to be like on a different thing. And for example, like this lemma, there is this really interesting lemma, for example, for any array, some array of some integers, there exists L and R such that so there exists some subarray such that when you sum up all of these AIs, it would be 0 modulo n, so modulo the number of elements in this array. So lemmas like these would definitely maybe come helpful in some problems, right? And today I would want to start with a lemma I learned, and I don't know like if you guys know it. I actually we took a look took a look into this lemma in the previous video. So the lemma I want to prove maybe, and to see like why it works, is the following. And then we're gonna solve two problems using this lemma, and maybe we will prove something. So let's first, what is the lemma? So let's just write it here, and let's see. Okay, this is some live scene. So what is the lemma? The lemma is the following. Why is it so weird to write? So my driver here somehow for the tablet somehow is like bugging, but whatever. So the lemma is the following: the minimum of x or no, I'm writing it stupidly. X XOR y and y XOR z is smaller than x XOR z for x for positive x epsilon z, like this. Okay, so this is the lemma. So given three numbers that are sorted in this way, so that are sorted increasing in an increasing order. So hello, Stefan. Given these three numbers that are sorted in increasing order, the XOR between some, like the pairs x and y and z, it will be, the minimum of these two XORs will be smaller than the XOR between x and z. So I don't know if you have heard of this lemma. I surely haven't heard it before. And here one thing to notice is that, just like as a thing, if x is equal to, if it has been like this, so with equality, it won't hold true, because it's like, if x is equal to y, this immediately means that their XOR is 0. And it just makes it complicated that this could be as well equal here, if they're all zeros. So kind of saying that, okay, we if I have added a number between x and z, this number will make a smaller XOR than the XOR between x and z. So this is essentially what it is saying. And this lemma is kind of very, very interesting and very cool. The proof of this lemma goes something like this. Imagine we have some x and some y number, which in the binary representation can be always written as, okay, so let's say this is x. I don't know, I'm just randomly writing some number. Doesn't really matter what. Okay, and y is, and z here, actually, like, yeah, first let's denote this as z. Okay, so z will be bigger than x. It means that, let's say here, instead of this, or let's say these are equal as well, and then here instead of this 0, in a z there is 1. And then here it could be anything, actually, it doesn't really matter. Why? Because this here, at this point, because this we say is the most significant bit, and this is the least significant bit, just for the reference. And this is in binary system. The trick here is that there will be some bit k, so we will denote this some bit k, such that this z and x differ at this bit k. Z is going to be bigger and x is going to be smaller. Everything on the left side is going to be equal. It could be all zeros. It doesn't really matter what is on the left side, but they're equal. As soon as something is equal in XOR, we know that this will cancel out. So Z XOR X XOR Z will give us some number where these are all zeros. Then there will be like 1 here. And then there will be, all of these will be some random number. That doesn't really matter. Something random here. But these are all going to be equal. Okay? But it's very important to notice this bit k here. This kth bit is very important for our proof. And essentially what the proof does, it says, I don't care about anything here. I don't care about anything here. I just care about this bit k, which is the most significant bit. So it's the most to the left side, where you have all of these are equal, and then like this could be like a garbage something, but this is like bigger than x's bit. So okay, so now we're going to add this epsilon, this y here inside between x and z, and this y is going to be so first of all we need to somehow, okay, so it's easy to see that, let's just copy out x and z here. And let's copy out z as well. I mean, this is z. then this was this. Okay, so we copied X and Z. Okay, so their XOR between X and Z, right, is essentially let's say this is the XOR, this here denotes the XOR between X and Z, this here. So this is 1, and then everything else here doesn't matter, some random things. Okay, now we're going to add Y into this. And Y, because we know that Y is in between these two, these bits will always be the same. Y, that's a nice pun. Why they're going to be the same? Because if any bit is changed here, it would be either smaller than X or bigger than Z. But we don't want that. So we proved by contradiction that Y has to have these bits the same. But now here comes the kth bit. So the kth bit, we can prove that if Y here had a bit of 1, his XOR with Z will suddenly be smaller, because here there will be zeros all the way, will suddenly be smaller than our initial XOR Z. Because here there's also 0. Here we don't care about these numbers. We just care that the most significant bit here and here is now changed. Okay, so this is one case. We proved for one case. Okay, what about the other case? What about when Y has here a bit of 0? This is also possible, right? So now in this case, the XOR XOR Y always be smaller in this case than X XOR Z, or is there a case where Y XOR Z will be smaller? Y XOR Z, this is Y XOR Z. This is the case where this is going to, if Y is equal to 1, then Y XOR Z is smaller than X XOR Z. Because this one and this one will cancel out. However, Y now in this case, Y XOR this here, X XOR Y is actually again some bigger number. So this is what I'm talking about. This is what I'm talking about. In this case, this is smaller. In this case, this is smaller. And whatever we take here, whatever we say here, this doesn't matter. This could be whatever here. Whatever we take as the kth bit in this Y number, it always will be smaller than this. So our proof is actually very simple. So you have to take a look first that these have to be equal in order. So this could be zeros. It doesn't matter what they are. But if there are some other numbers, they have to be equal until some k bit, which is not equal. Why there will always exist a k bit such that X and Z differ? It's a very simple proof. It will always exist a k bit in which X and Z differ because X is not equal to Z. If X is equal to Z, then only in this case will there won't be like k bit that differs. Okay, so very cool lemma, right? Very cool lemma. Yeah. So the thing is now, okay, we have this lemma, right? So what kind of problem does it use this lemma? And if you have watched my previous video on AtCoder, we have solved A, B, C, D, E, and F in about 15 minutes. And then I was stuck in G, and G was essentially a minimum XOR pair query problem. And this sounds like a data structure which I would love to solve, right? It sounds like a data structure problem, and I just spent a lot of time. Then something with the camera froze, and then I just gave up because I went on a totally different and totally wrong direction. that's my fault. So essentially what the problem actually requires, here I will send the link in the chat just for like that. So this problem like requires, you can write you have some queries here. So you can write an integer x on the blackboard. You can erase an integer x from the blackboard. Always, it is guaranteed it exists. Hey Umar. So we're solving some AtCoder problems. If you want to know more, you can just rewind the stream on YouTube. It's saved, so I don't have to explain. But yeah, so essentially we have like two types of queries. We have write x on the board, erase x on the board, and print the minimum possible bitwise XOR of two integers that are written on the board at this moment. So the minimum possible bitwise XOR of the integers. So because here the minimum possible XOR of two integers, if I have, so we know this lemma is true. So we know this lemma is true. And it says, okay, this lemma holds when y is in between x and z. So this lemma with a simple induction proof, of course, can be extended to something like this. What if I have integers a which are all like this? Which are all like this, right? And these all integers. So the minimum possible XOR will be, because this lemma is, we know we can take any three integers and we say that the XOR between these two integers or these two integers will be smaller than these two integers. We can extend this with induction. We can always take only the adjacent integers, and we know that the XOR, the smallest possible XOR, will be some XOR which are like either this or this or this or this or this. So it's like there we can show with contradiction. There won't be the answer wouldn't be like a pair this and this. This problem just requires this property, but I could not see this during the contest. Yes, I could not see it either. Like I didn't. I quite during the contest. I quite mostly thought that that this problem required some try. Because always when you have some XORs and you want to find like the my internet connection is a bit small, so I'm sorry if it kind of wobbles, but so the thing is that when you see XOR problems and some data structures, it is sometimes like my brain goes to a try. Because there are these problems where you search into the try for some XOR that is very similar to your to some number that is very similar to your number, and yeah, so with contradiction we can show that if I take here some two numbers that have some number in between, and I say, okay, wait, why wouldn't the XOR be this? Why wouldn't this be the minimum possible XOR? It's because, okay, let's go to the lemma and let's take any of this here number, and now all of a sudden either this is the most possible, this the minimum, or this is the minimum. And then here you could see this recursively going throughout the problem. Can you go over the contradiction proof for why the minimum XOR will come through adjacent? Yeah, this is what. So let's just. So the trick is always with to find some induction step. So the induction step is is this: if I take these two numbers, then there will exist some number in the middle such that this is the most, or let's get some here, let's say this and this number. So let's take this number in the middle and we say, okay, this here has smaller XOR, or this here has smaller XOR than this XOR. So we can immediately kind of remove these two numbers, this pair here. And then you do this proof for these two numbers, and then there's a number inside, and then there's a number inside, and you will always end up at a number which is end up with these two here, with adjacency. So however you want to make these numbers the minimum XOR, with this lemma, they will always end up at an adjacent number. So I think that's a proof. That's like kind of verbal proof to think about. Always, if you have something like this, you just try to see, okay, this won't be true, and then actually it comes out to won't be true, right? So if this proof is not, maybe it's not formal proof, but you could for practice do even formal proof and say, if there is let's denote a function first, because induction proof, somehow you denote some kind of function and you denote some kind of base, and then you try to prove this function but always when you're on competition, you don't have this time and this resources to just write, okay, I will prove a function f of I and j, which means that the XOR is equal to AI and XOR AJ, and then blah 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 blah, some things that that are not important right now. So okay, so we got this. So there will be like adjacent numbers here, and then the trick now is only like how we're going to manipulate these numbers into having the data structure. So you could insert number, you could delete number, and you always want to have this minimum XOR here at your disposal. So I haven't really thought how it's the best to implement this, but also like I would want to shout out like a the try data structure. If you haven't heard till now the try data structure, there is this problem on CSES, which I think I solved. For those who want to some practice on one more XOR problem that actually doesn't require this lemma, but this problem is very well known for a try problem, maximum XOR subarray. I will just give try XOR problem. I will just give it in the chat, just for those who maybe as homework want to try something with some different data structure and XOR. This problem also I thought about solving with try, but it's a lot more complicated. So in our solution, so let's go back to our solution. I will just delete this try. I will delete this. I don't care about this, what I have wrote. So in our solution, we just need to kind of keep with the adjacent numbers. And if some number is deleted, then there will be so if some number is deleted, then the adjacent values that this number created with some other numbers should be also deleted from a set. So there should be a set where we keep the adjacent values, and there is it well zoomed in? I think it's well zoomed in. I think right. It's okay, but there also needs to be some multiset probably where we keep all of the numbers, and this multiset will be so this multiset, let's say ms, I don't know how to call it. So this multiset will, so when a number is inserted, we will insert it into the multiset. We also need into the adjacency set to insert two things. If there is a number smaller than this in the multiset, or if there's a number bigger than this in the multiset. Or not in the, actually I will use a map, not because I could, in the map, what you could do is, it's, I think, easier implementation per se. It's like I could use the inverse, the reverse iterator and the next iterator to find the number that is like immediately adjacent to this number and immediately behind, immediately smaller than this number. So I would say like this. If so how do we say previous of so auto it is np find x. So I will find this is the middle, this is the inserted number, and then I will say previous from it, if it is not begin, map begin, so it's not the first number, there always will exist some previous number to match with. So previous of it is the previous number, and then this number XORed, we will need to dereference this pointer, XORed with my X should be added to the adjacency to the set. Oh, maybe I have to access this as first. So first is the number, second is how many occurrences this has. So this is essentially adding to the set this number. So let's just, for good measure, let's denote this as L. So this is my left number. If it is, so I would say next at it is not mpn, so it's not the, so the next element is not, it does exist in the map, then the right thing will be this, and then in the adjacency list I need to insert the right thing. So this kind of adds and deals with this. Okay, so this is one thing. Another thing we need to keep track is to keep track if Boolean, and then we kind of want to keep, do we want to keep track about is there this edge case of having the edge case of having the so there's this edge case of like, what about 0? So what about if there are duplicate numbers here on the whiteboard? So there's this edge case of duplicate numbers, gives the answer always to 0. But also I'm thinking, is that the best way to implement it? Because now what happens if we have two XORs here in the set that are, so how do I delete a number? So when I delete a number, I need to also delete his connections with this number, with like these connections. And the best way maybe to do this is to how to keep track of this. Are there any good ideas for that? Because if there, can you just do it with a set? I don't like with this. I kind of don't like sets because they're. This could multiset. I mean, yeah, multiset here on the adjacency. Yeah, of course, on the adjacency, a multiset could be nice, right? It should probably be a multiset here. But also, do I need to add the reverse thing here? Do I need to add it? So x, when x is added between some numbers here, instead of the map, yes, you could do the multiset. Yeah, instead of the map, you could do a multiset. Is that does that simplify the? So that kind of simplifies the edge case, right? So there's no problem with this edge case if there's a multiset. But also we have to be careful about. So that I have like this function erase1, which is called. And this function is just a snippet that finds this iterator and then erases it from some given multiset. So this is kind of a function to erase one element from the multiset instead of just calling this erase on a value, because erase on a value will erase all the elements given that value. But yeah, so let's assume that this edge case is fine with given the multiset. Now previous and these won't have a first and second iterators, so these would be just dereferenced. Now when you add an x, this x will add a connection through A, and this will add through B, right, like that. So this will just add this edge and will add this edge here. So what if I erase A here? This edge here is a symmetric, so there is a symmetry. A XOR X and X XOR A is the same number. So this allows us to just keep adding and erasing however we want, however we like. So essentially on the erase side, what we will do is we will of course from the map here, we will erase one from the map. When removing, just do the same, but yeah, of course, that was my point. Erase one from the map, and then I'll just like copy this here. Actually, I will erase it at the end because I need to find where that iterator is. So what happens if there are multiple things that this function tries to locate? If successful, turns out if there are multiple things in the multiset, will find like the first one. I'm not sure about that one, but okay. So if this is the case, so instead of here insert, I will just erase one adjacency L, and here I will just erase one adjacency R. So erase one R from the adjacency and then erase from the map, and at the end I will just print the first element in the adjacency is like the minimum one. So here it didn't quite work, but let's see. So here, what is this element? 2 is being inserted, is being erased. So So the erase is not working. Fine. Okay, so 2 should be erased. So you find this iterator, then shouldn't you also add to the adjacency with the values they're going to be next to each other? To the adjacent, I'm adding the edge between x and its previous element and the edge between x and the next element. But yeah, when you have like multiple elements, it becomes a little bit nasty. If we add a 3, then that would be like putting in the end. And then yeah, okay, I get it. I get what you. Oh yeah. So when you remove an element, here, you want to add. So you erase one and erase here the left and the right side, but you want to add from the left and the right side this element. But yeah, so like that. So from the adjacency, you want to kind of insert LX or R. No, it's not LX or R, but the previous. So we take the previous and the next, and then we XOR these two together, and then in the adjacency list we want to insert them together back. Taking XOR suggests to be removed. Yeah, but one XOR, like this will never be in the adjacent. One XOR, so 1 and 3 will never be in the. Oh no, like I don't like the duplicates. I don't know what happens with the duplicates because of these iterators here. Kind of don't know. I don't know multiset enough to. But what you're saying here is these are my elements, these are like x's, right? And the adjacency matrix looks like this. Like this is the adjacency set here. And then when we have this adjacency set, if I delete this 2 here, it's not the same as I delete this 2. Or is it? So if I delete this 2, this adjacency will be deleted, this adjacency will be deleted, and there should be added like another adjacency here. So that should be fine. It's not the same which 2 will. Technically, it's not the same which 2 will delete, but in the end, it's kind of the same. Yeah, that's the point what I want to do here. I just want, okay, to insert, I just want to see if I made some mistake here. Yeah, so I'll just print out I will always print out the after the first, so this is about which query is this? This query is this. So this 1, 2, 0, 1, 2, 3, 4, 5. Fifth query. After the fifth query, there's 3, 8, and 9. But the elements are only 10, and there's more elements than. The problem is if we have 1 and 3, and if we remove, we'll have so at first we have 2 and 10, which is fine, and then we add a 3 here, and after the third query there are 3 numbers, which it isn't. Yeah, so that shouldn't supposed to be, because when you're adding a number, you should like erase the number in which these 2 XORs happen. So I get it, like you need to erase this number here. So you kind of need to erase that, and then like, I mean, yeah, just the implementation. Just now it should work. Or no, maybe no. Okay, now this is 2 numbers, that is correct, and yeah, I know, I should call it to remove. I know I should call it to remove. I'm just thinking about what happens here when you erase 2 after the fifth query. 0, 1, 2, 3, 4, 5. After the fifth query, when you erase a 2, and there will be only there should be only 1 number left, and yet somehow it's not. So when you erase this here too, I know there's that I never learned, like, I mean the F2 here, when I go F2 and I type to remove, if there is a, so now it will just give me these here. You can select what you want and just do D, Control D, but wait. But this doesn't know that this is inside the block as well. Like, this knows that this is connected with this, but that this is not. Or you need to select them all with the multi-cursor, or no? Like, there's this F2, and then you could do like to remove, but this looks like this goes through all of my codes and sees what else I can refactor, and then it like shows me all of these. But if like there is a file that has the same name, it will just like pop it out from other files, and I'm so scared to use this because there could be like some file selected that he thinks that it's like somehow related to this file, and like replace them there as well. So it's just so not I don't know. I don't know how to set it up so it just looks at one file, but like something refactor settings or something should be. I will try it later maybe in the refactor settings. But I want to see why this leaves here a 3 behind when you erase 1 and 1 from this side. You also want to so of course, so there could be such that there is no element to the left side or to the right side. So there could be this idea. So there's no element to the left and there's no element to the right. Does it kind of mean that if that's the edge case where like you delete this element and then this is not like this shouldn't be inserted. So if like both this should be inserted. So how do you and this should be inserted. I think when they're only both, this should be inserted. Oh. Or deleted. Yeah, I think that this kind of works here, right? So this passes. Should we submit just for wrong answer, or should we maybe try to? I will just submit it. I don't know. It's not the best code, but. Oh, I shouldn't have submitted because like I have like all of them accepted in the first run. Now if there's something wrong with it, I'll be so frustrated. Okay. Please don't be wrong. Yes. Okay. Yes. Just like okay, that's nice because like I have them all in like the first run. I don't want to break the spirit, you know, like that's what I want to. Okay, so what actually problem? Yeah, actually EX I need to like upsolve, but not today because today we're going to take a look at some like one more problem that uses the same lemma but kind of in a different way, I think so. I'm not sure, like, I'm not sure about the problem. But yeah, I will try to come up with some solution. I haven't looked up the tutorial on E yet, but I don't know. But this kind of looks good. That this could be actually done in some like data structure, maybe just like polished up a little bit. This erase and delete here. But okay, that's cool. That's cool that this problem works that way. So okay, so the other problem is this. I don't know, you may know this problem. But I think I can solve it in the same way. With the same lemma. But I'm not sure, I have to prove some things. So this is a 2300 problem. It's I think the same difficulty as apart from upsolving, what should I do to solve more than 5 problems at beginner? At beginner contest, the trick is that like the first 5 problems is like maybe the first 4 problems are very easy and solvable, like just code it. There's nothing in the problems, and then the E and F. And what I did is actually, like on Kenko, what I did is I went like solved like a lot of D problems, a lot of F problems, just for a lot of E problems. I want to solve a lot more F, but now it becomes apparent that in the last like couple of contests, these have been much easier, maybe problems till G. So I don't think there will be like I think it's just practice. It's just practices. What is this rated about? 2000 rated problem. So if G is 2000, I remember when, like, let's say here, like G is 3200 problem. There's no way to even try to solve this problem. Or here even these used some, I remember, some like max flow algorithms and some modifications to zeta transfer functions. I don't even know how to begin, but if you like just go through Kenko and maybe solve E, like just go through E's and then solve them, that would be good as well. I need to upsolve these, but I want to solve this because I think it kind of uses the same technique, but I'm not sure. So it says you're given a complete undirected graph with n vertices. A number ai is assigned to each vertex, and the weight of the edge between vertices I and j is equal to ai XOR aj. And then you need to calculate the minimum spanning tree in this graph. FFT, so don't do FFTs. I can show you problems with FFTs, but just don't do it. Okay, so a number ai is assigned to each. So the edge has an XOR. So if you could imagine the graph is a complete graph. And let's say the numbers are like in the test case. And their edges is like, okay, this is XOR, the edge is 1 XOR 5, which is 4. This here is 1, this here is 3, this here is 1, this here is 7, this here is, come on, what is this, 2? No, 6, right? Then this is what? This is 2, this is 7, right? And what else did we miss? 1 and 4, 5. Did I miss something? Yeah, I missed something here. But this is 2 and 4 is 6 again, right? So now that when we got this graph, the minimum spanning tree of this graph is maybe this, then this, then this, then this. So the minimum spanning tree is 1 plus 1 plus 2 plus 3, right? So this is like 7. Is it? No, it's 8. Wait, what? Did I mistakenly draw? Yeah, link to the problem, okay. Did I wait. This is the 1, 2, 3, 4, 5 case, and it's 8. Wait, this is not 2, this is 7. Wait, I'm dreaming something. This here is 4. But then this is 9. Oh yeah, okay, oh, yeah, of course. Like you use the 2 here to get here, and then you use this, and then this is essentially 1 plus 2 plus 4 plus 1, which is 8. Let me just sort the elements and sum the XOR. Yeah, I thought about that. I thought about that as well. Like that was my first thought. Wait, can we just like sort the elements and just like sum up the XOR of adjacent values? But actually it turns out no. It turns out no, because it's like, yeah, first like you see this contra example that like you have here it's 8, and then you have here without this 5 is essentially again 8. Now you're gonna say, wait, what? Like when I delete 5, I delete here an XOR of 4 XOR 5, which is 1. I should get like 1 less 7. But that's not the case. But now that you know the lemma, is the lemma actually I think is going to help us solve the problem, and I'm going to say like I haven't looked up the tutorial. I don't know like exactly how, and I don't know even if I'm right. So I could be totally wrong, but what I'm thinking of is something it's something similar to what Blogway said, but in a much more like just much more algorithmic way. And essentially, if you could see, if you know how a Kruskal works, right? So how Kruskal works is it sorts the edges. So if I have the complete graph, in which I cannot have in this problem because complete graph is too big. But if I have, I could imagine I have the complete graph. Then I know that the Kruskal will sort the edges by size, and I know that it will actually pick these smallest edges here first. And then, okay, it will see that this 3 is already used, so between like this and this is in the same tree already used, so it won't pick it, and then it goes 4, and then it will pick it here. So it kind of says that, okay, I will use first the smallest edges here, and then somehow I will use these bigger edges. And if you see how it relates to the problem, it actually like, okay, first you use this adjacent edge here between these two, and then you use this adjacent edge between these two, and then this edge here, 1 and 3, is essentially because 2 is being somehow like, you see, like used with this 1 here, it's connected to this 3, and then this 3 it's connected to this like 1. And then again on this way here, this 1 connects to 5 because all of these have been inside the, so all these are like connected, and then 1 can jump to 5. But so the same idea about Kruskal is starting from the minimum and working your way up to the top. The same idea here. Wait, this problem is from 6 years. Yes, so this it's not really upsolving right now, but it's actually a problem that is connected, I think, to this minimum XOR pair query, and I want to like just for good measure maybe solve this as well. Because it seems like an easy and educational problem. It seems that like you could learn a lot of stuff by doing this problem. Maybe we're going into the total wrong direction, but at least I have something to connect these two problems. So what I was thinking about is, okay, so the adjacency, when I connect them with an edge, if if I make it 1, 2, I saw the tutorial if you want to know what algorithm is. No, I don't want, like, I want to, I really like the problem. I really like the problem, so it kind of wants to steer myself into, even though if we don't succeed in solving it, I could just look up the tutorial and maybe go from there. But what I was thinking about, okay, we know that the adjacency values are very small, and the smallest we have proven that the smallest number to start off is some adjacent value. We have proven by the lemma. So we know where Kruskal will start. Kruskal will always start through some adjacent value, and we know that these two will be connected with our algorithm, and these two will be connected with our algorithm. But connecting them kind of says that I could just so this one here, I see that the adjacency of the one here to 2 is some 3, right? Some 3 here. But we say that 1 to 3 is 2, this edge. So I'm thinking about, the thing is this here, which, like, when we connect these two pairs, I'm thinking that actually there could be, wait, so I'm kind of thinking about skipping up some things. So I know that these are 2 connected. This 3 will skip these 2 and now can connect to 1 as well. Know that this is the minimum, this is the minimum. So we said the following idea. We said that the minimum of XOR, we said that the minimum, just maybe just a few minutes I would use just to try this. We said the minimum of these is smaller than X XOR Z, right? Okay, we know that this is smaller. Yeah, the middle elements have 2 choices. So it's either this or this. And then you could kind of but can you always say, is there a proof that you could always say that, like, given some elements, let's say some elements, no, let's say that this is like 10 and this is 12. So is there always some configuration that the middle elements pick either left or either right side? Wait, so no, that means no, because I don't think that's the case, because if like you pick this side here, if you start by picking this side here, you could easily say that by this law, this is smaller XOR than this XOR. So it could be the way that like you always pick like this, which is not kind of the case. There could be something like that where this here is left unpicked. So the Kruskal will definitely start from adjacent XORs. So that's the most minimal thing. And then when we start from adjacent XORs, we now kind of say that I would think so, that now we kind of look at this element and say, okay, can we connect this element to this here and maybe this to this here? Then when we say, okay, this will be taken, then you kind of look again and say, okay, can we connect this element to this? But that doesn't make sense, because here this element is technically connected to 5 as far as I know, right? So kind of you will start from adjacent numbers, but then you kind of jump. So I don't think can we prove something with this here? So I think the lemma is, I think you're right. I think that the lemma says that the middle element first of all, I think about sorting. I think that sorting is required. I think sorting is required, and I think that the requirement that you kind of are right. So let me try to prove this, that every element here in the middle will either will be in the spanning tree, will have an edge in the spanning tree either to the left or either to the right. Can we prove that? Can we prove this hypothesis, this conjecture? This conjecture is what Umar said. Middle elements, so from I bigger than 0 and smaller than n-1, there is an edge either to like I-1 or exists an edge either to I-1 or I+1. And these are like 0, 1, 2, 3, 4, 5. So I don't know my internet connection. I need to grab maybe some cable here. But okay, so can we prove this conjecture? Can we prove this conjecture? Is it the right thing? So what about, like, okay, proof by contradiction. So let's say this is not true. So there exists some element. There exists some element I that is not connected neither to this side nor to this side, so it's connected to some other side here. So it's connected to some XOR, some other XOR, which is like I plus K, and K is bigger than 1. Then this XOR here, it by definition, by our lemma actually, we kind of return back to the idea that, okay, there exists in the middle an element whose XOR is minimal, it's smaller than this. So we will never take this edge. We will always take an edge which is like through an adjacent element. Yeah, we will never take this edge. We will always take. So, kind of, I think you're right. I think this kind with contradiction, this proves that each middle element will be either have an edge on the left or an edge on the right. So, okay, let's assume that this is true. Then means that after we hook up all of these middle elements, there will, wait. Yeah, so we kind of will hook up something like this. So some paths, right? Let's say something like this. And now you need to hook up whichever XORs between these paths. Here it becomes a little bit more complex, maybe. For each of this here, would be actually there won't be any paths like we want to build an like my goal is, what I think about the solution is that you want to build some algorithm with priority queue where you would put the edges into the priority queue. So my kind of algorithm would be the following. If I have a graph, it doesn't have to be a complete graph, but let's say it's this graph. Doesn't really matter. So my kind of algorithm is, okay, you start with like the smallest edge. Let's say this is the smallest edge, and then you put these two nodes, like you put the you take the smallest edge. You have some DSU here, let's say. Do you have like I don't know, do you guys have some problems with the stream? Because it says here that it falls out, the quality sometimes falls down. So if you have some problems, I may wait, the internet is so let me try with this Ethernet here. So I don't know, but I think for now I will try next time to fix the internet connection here in the workshop, because here in the workshop I'm like more free to discuss and to stream. But apparently the Ethernet cable is not hooked on, so this is what we have right now. But it should be it should be true. But let's say that so my algorithm was this, like, okay, so you go here and you choose the minimum edge from the. Okay, so Umar has like some contra example to my algorithm. Consider the edges 1, 2, 3, and 4. I don't know, like 1 to 2 and 3 to 4 or what. I kind of no, I'm not talking about now this concept per se, this problem. I'm not talking about this. I'm talking about the general case. Yeah, the nodes 1, 2, 3, 4. 1, 2. If I take a look about this problem, the nodes 1, 2, 3, 4, then what will be like the minimums? So here there will be 1. Definitely this would be taken. Then here this would be taken, I guess. And then with 4, it is the most responsible thing to pick 1. And this is the minimum spanning tree of 8. Like the ending nodes are kind of an exception, because they don't have like they can't be cancelled out with some other node here. But these two nodes kind of connect with but what I was saying about this algorithm, what I was saying about my specific like minimum spanning tree algorithm, what I was saying is that consider we have this now tree here, and I will add the edges here that of my nodes in the spanning tree in some priority queue. And then from the priority queue, I will always pick the edge which has the minimum weight. So the minimum weight, let's say like this here, to this node here. This is the minimum weight. And then on this node, I will add again all of the edges in the priority queue. So this here, the dashed edges, these are in the priority queue, and these, like, I will call like a frontier or something. Like in geometry, you have some like frontier, and then you just think about these numbers. And you could easily prove this by, you could easily prove this algorithm why it will work, because if you have some spanning tree that is not the spanning tree of the graph, but is some like other spanning tree, to create the whole spanning tree of the graph, there are some other nodes which are not in the spanning tree. Let's say like this, doesn't matter. There will be always some edge that kind of connects some node with my spanning tree and with the spanning tree of like the graph, of the other part of the graph. So I think this algorithm of like keeping this frontier of edges, keeping this frontier of edges in a priority queue instead of what Crucial does, which is just sort the edges and then use DSU on them. I would have the edges in a priority queue and then just like add specific new edges into the priority queue, and just from these edges take out the DSU. And if you could imagine this in like a complete graph, what would this be equal to? This would be equal, so if you have like a complete graph, which we have in this problem, right? So we have some vertices, doesn't really matter which. And we kind of picked, let's say we picked this edge as the minimum because it has cost 1. From all of these edges. So now these two here, I kind of wanna add all of the edges from 2 to every other vertex that is not being visited in the graph, and from 3 as well. And then pick again the minimum edge here. So let's say this is the minimum spanning tree, or let's with blue color. And then let's pick that, okay, we think that this is going to be the minimum edge from all of these, which is not true. This will be, but let's say that this will be the minimum edge. Would be 2 to the 3 would be added first. Yeah, the edge between 2 to the 3 will be added first. Yeah, that's correct. Yeah, that's correct, because it has the minimum cost. But this frontier, this kind of proof here, it's like if you have all the edges, that one of them has to be added. So what I'm thinking about, okay, we add all these edges, this edge, and then all in the priority queue we need to add all of the edges that now the new node has. But this is quadratic time, so in our case it's just like quadratic time, I think. But I think with the bits, there will never be an edge that goes from a node which has like, I think it's about the kth bit or something, because there will be never an edge that goes from a node to some like huge node, from some small node to some huge node, because there will be inside a node which the huge node can jump to and get a lower XOR. If you know what I mean. So if I have like some nodes which all of them are like this, there will be some edges between them which will add first, let's say. Then this node here will never go to some other node here, it could like jump to some other island here, because this would be a smaller XOR. Because what we said is, if I have this node, if I have this node, and I have this node, this would doesn't even matter. Like this could do. I mean, you see, the lemma here still holds. If I take these three nodes, it's either this or it's either this. It kind of holds here. So let's say it's this, and then I take some other three nodes, and it will still hold. So I don't know. So here it says like constructive algorithm. So it gives a problem tag about constructive algorithms. I kind of don't. Constructive algorithms usually take into account some, like if we're talking about constructive algorithms, they usually take into account some specific thing which can be then induced upon the whole graph with like without removing and putting in and then like putting in and removing stuff. It's just like there is some property that just constructs the graph with this property. And this, the lemma is like really close to some property that we need, as far as I can think of. So as soon as we have three nodes, as soon as we pick three nodes that are like this, the minimum would be either this or this and never this. But what if, like in this case, if I pick this node, and this node, the minimum of all of, like if I pick this node, and this node, of course here there's like 3, here there is what is this, 6, right? And here there's like 5. So of course this makes sense to connect these two here, but also makes sense to connect these two. Because this is a smaller minimum. So this is where it kind of concerns me. But I would think about like jumping. So should we see the tutorial? Should we see the tutorial about this problem? Or maybe like there are multiple ways of solving this problem? Does Blackwood, if you're here, can you give us some hints? So I would think about like a kth bit. So I would think about how this relates to the kth bit. Can we get so the kth bit? There is some number with, for each bit, maybe take a look at the graph separately. So you say Borufka's algorithm. I googled that once because it was on the, so that's I think there is Borufka algorithm. I think there is this, I don't know exactly, no, not this. There's this from this guy Pashkar. How was it, like, which does like data algorithms and data structures on Russian. I don't know how it's on Russian, but let's just see what it does here. Each component. Wait, just I don't know the Pavel Mavrin. Yeah, thank you. He had a lecture on it, I think. Yeah. Was that? No. I think he had some lecture on it, which I saw. But I didn't actually see the lecture. That was the problem. Like, I thought that I will never need that shit. But the following is called in the conditional clauses, every edge UV is considered cheaper than none. The purpose of the completed variable is to determine whether the forest f is set to span. Wait, can I see a code from this? Let's see in the EKZ library, does it have some code for it? No, it has for Kruskal, so... Like, when I see code, I can just more visually understand what it does, instead of just this. So, okay, so you have you have some DSU, which is not important. And then, okay, we have some subsets, and then it says number of trees is bigger than 1. Okay, so this is the number of components. Traverse through all edges and update cheapest of every component. So the goes through the graph size. Find set. Wait, graph size is what? Graph is like all of the edges or what? Don't quite understand this. Time complexity of but no, we have a lot of edges here. The time complexity of Baruch's algorithm is E log V, which is the same as the Kruskal-Supreme's algorithm, but we can't Baruch used as a step in a faster randomized algorithm that works in linear time. Okay, let's understand it. Even though, like, I don't think the algorithm is just like plug and play. I think it's just the idea of this algorithm, maybe. If two corners of the current edge belong to the same set, ignore. So we kind of go through all of these edges and we say, okay, we have these, then cheapest, we find the cheapest edge between two. Consider the above picked cheapest edges and add them to the sorry, wait, I want to understand this, but if edges are distinct weights and so while not completed, find the connected components of F and assign to each vertex its component. Initialize the cheapest edge for each component to none. For each component, so for each tree that I have right now, I have the cheapest edge to none. For each edge, so I go for each edge and then I kind of see if they're preferred in these components. Okay, I understand now the algorithm. Now I understand the algorithm. So it's essentially this here takes log steps to compute. This for loop here takes log steps to compute because it will always merge. In short, you have to start with n components. For each component, find the cheapest edge going from that component to some different component. Then take all these edges in the MST to getting larger. Am I correct that this step here only goes log n times? It just only like operates log n times? Because we're going through each edge here, UNV in different components, this step kind of seems log n times. We will always like merge first like by 2 components. Like first it will probably like having all of these, we will merge like some things in 2, and then now we will have n divided by 2 components, and then for all of these I will like somehow merge them. Now I have n divided by 4, and now then all of these I will merge somehow, and then there's n divided by like 8 and so forth until it goes to 1. So it's, I mean, or seal or whatever. Okay, so that I kind of understand. Okay, so that's a different algorithm than what I kind of thought of. So that's kind of cool. Okay, so how do we implement it in our task? So log n steps or less, if you're lucky. Yeah. So how do we implement this algorithm? Because we have too many edges to go through all of them. There are n squared edges to go through all of them. But this lemma maybe helps us to narrow this down. Instead of going through all edges, we could just go through some like valid edges. Maybe through some edges that we actually need. Okay, so for each component, so we have some component. At first we will have like this. So at first we will have only 1, 2, 3, 4, and 5. But now how do we pick in which edges do we go? Because there's n squared edges, we can't just iterate over all of them. We could so can we get some kind of the XOR? So like there's AI XOR AJ, right? This kind what if I want to find a pair? First, like I go through like the smallest. Which pairs have an XOR of 1? Which pairs have an XOR of 1? Like you could, they have an XOR of 1 if they differ here in the first bit, and each other bit here are the same. So it doesn't really kind of matter here, but this has to be like this, they have to differ here. Interesting. Okay, so they have to differ there, and yeah, so x1 and then so I could just count them here until and just, but isn't that more like isn't that's a lot of complexity, right? Okay, so the first step is to ignore duplicates. Second step is to ignoring duplicates, because duplicates can be connected with XOR of 0. The second step is, okay, I can count all of these here from 1 to like n here in this bit. So I could just do this 0 0 0, then I could do the 0 1 this, but the problem is that not everyone is going to yeah, the problem is that not everyone okay, I have another idea maybe, but I don't see how the Borufka algorithm can be used here unless you somehow get the edges down. I don't see it. I honestly don't see how it can be used. I see the logarithmic timestamp, that you need logarithm times to like compute it, but still doesn't make sense. Because if you could imagine that one value has, we kind of need divide and conquer on the edges or something to then compute this. So do you have, like, guys, some tips, maybe some interesting ideas we could try? We could try to is the intended solution to the problem, but there is another solution that doesn't use the sound. Like I'm trying to figure out how to iterate over these edges without making more than n steps. Like for each of these, for each node, there will be like the smallest edge we could find. And we kind of proved that like the smallest XOR will be like some adjacent thing to this node. But when you kind of get this smallest XOR to this node, then the other XOR is really big. Actually, can we prove one more lemma here? Can we prove that the maximum of this is bigger than this? Does that hold? I don't think so, right? Like, does the following hold? with the same idea that proving to the kth element here, to the kth bit, the same idea, we know that y will be, so let's say y is 1 here. So let's say this is the same thing we did, the kth bit is here, these are all like, let's say some same numbers here, the kth bit is here, and the maximum XOR here, in this case this, is it bigger than this? Not necessarily, right? Because you could have not necessarily, because you could have like this here, and then you could have like 1 here, and in this case this this is 0 in the XOR, but this and this, the XOR is 1, and thus actually this doesn't hold. So that doesn't hold. That doesn't hold. Okay, so that doesn't hold. So that's kind of interesting log-n times to do that, but I'm not sure. I'm sure that Pavel had you don't have to do it with Borovka. Yeah, I mean, it can simply be solved by try with 2 keys, 0 or 1. By try. Okay, that's an interesting conclusion. That's a very interesting thing. So it says, okay, so that is kind of correct. That is kind of correct, if you think about it. For every number, we need to find like the minimum edge that connects this number to some other number. And when we find this minimum, we could put all of the other numbers in a try. And then we iterate through the try and we find this minimum edge that connects some other number. We connect these two in the DSU. Afterwards, we delete this number from the try, and we kind of iterate through the try again to find some other number with the smallest edge. And then again, so this is wait, isn't that essentially what I'm saying here with this algorithm, with like the priority queue? Instead of like having a priority queue, like you have a try. And like the DSU is not important right now because like, yeah, actually it is, right? No, it's not, because in the try there will be never a number which is in the minimum spanning tree, and thus this will hold true. So yeah, essentially it's the same algorithm I'm saying with this frontier, but without the priority queue. The priority queue is try. So we could call this. We could call this. I don't understand the Borovka's solution though. The Borovka solution is I understand what Blago said, but I don't understand the Borovka solution. And thus I will call the try solution. I will call the try solution because like I like tries. Try is one of my favorite data structure, and I will say that maybe actually, like, is it my favorite data structure? It could be my favorite data structure. Like, I understand what's the idea behind the solution. I think at least I understand it. If I'm wrong, like, correct me on it. But it should be like really fast. It should be extremely fast. What was what you said, like n times the maximum the log of AI. And I will just call it right now and then like explain maybe in more detail, or like when I will be calling it, I will explain how I think about it. But always what I do is I have some children here, which I do like null pointers. In the try there will be two functions. There will be a function of insert some node, and then there will be a function of like remove. I mean, not extra. Not remove, like query. This function will query and remove the node at the same time. Also, there should be count. Also, should the try be equal to? Yeah. So I kind of understand what he's saying. Yeah. So I will start like this. I will go on each of the numbers. For each of the numbers, I will create a try. Each of the numbers except the first. And then essentially what I will be doing is I will be taking this number off and but is that correct? So solved by try. So let's see. Let's just take a look at this. So a binary try will have will look something like this. Something like this. And these here edges denote that either you have 1 or you have 0. And I always start from the most significant bit, because the most significant bit will change most of the of either on the left or on the right. It will change. It will influence the most. And then I do this, and let's say these are all ones here, and let's just not do that, but let's just like do this. This is 0, 1, and I mean here it could also be something like this. This could be 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1. Doesn't really matter. And then you iterate. So these are all of the things. And then if I pick like one node, let's say the first node is 3, right? Say this is the input. All of these nodes will be inside of the try. The problem is given in the chat. I'll just get the link again. So all of these nodes are inside the try, and then we know that the 3 has to connect to all of these nodes, has to somehow connect to them. And then we find what is the minimum edge from 3 to some node here. Let's say the minimum edge to some other node here. This is not the minimum, but let's just say it is. Like nowadays, everyone can say something, so like we're gonna say this is the minimum node. So to find it, actually what you do is like you traverse the try down, and if there's, and you take a look at 3, and 3 actually has like 0 here, and you want to have 0 here, and you want to have 0 here, and then you have, oh, here you have 1 and you have 1, and then that's 3 here, and then it means that there's some 3 here. So you kind of connect these two, right? So into the try, and now you kind of want to delete this 3 from the try. So you want to delete that, and you delete it to here. So now here this is deleted, but the minimum spanning tree now looks like this. Now we don't really know the minimum spanning tree. Does it go from here? Does it like extend from here? Or does it extend from here? Or maybe it extends from both sides. And that's what I'm a little bit concerned right now. So how do you know from which side does it extend? Because the minimum spanning tree can actually like extend from here to here. Maybe. One more time. It doesn't need to be actually from here. If that would be like a different number here, it does make really big sense. Does it extend from here or does it extend from here? Maybe you iterate again over this and over that, and then you see whether or not you could. Do you iterate again? But then, okay, let's say you connect like this, right? Then what do you do? So you delete one more, and then do you iterate again? You can't iterate again from all of these. You kind of wanna what does the edges represent? What if you have like 2 tries, or like one try which has like, which is a little bit smarter, in fact, that like if you have like try which is the elements that are not in the segment in the spanning tree, and one try that the elements are in the spanning tree, and then what do you do? Then you can... No, you can't do anything. I don't quite understand how to deal with this. Don't quite understand. Let me just... Can I read some editorial or something? During each iteration, we find the connected components in the graph formed by already edges. And for each component, we find the shortest edge that leads out of this component. Then we add the edges found to the number. This only explains the Borufka's algorithm, but it doesn't explain how to do this. However, in this problem, we need to speed up this algorithm. We can do each iteration by using a binary try. Oh, so you need to use both the Borufka's algorithm and a binary try. We can store all values a in a try. When we find the shortest edge that comes from some component or vertex outside, we first remove all values contained in this component from the try. After that, for each vertex in the component, we can find the closest vertex outside. That is by descending the try. And then we insert the elements AI belonging to the component back into the try. So it's actually nlock this. You can only do it with the try. In fact, I don't really understand what the tutorial is saying, but that's okay. Just make a binary try and all of the AI. So okay, put all of the AIs in. Then for each subtree in our try, we need to know the minimum cost to conjoin everything in the subtree. For each node, we store the minimum, of course, the minimum cost, because everything above the subtree is 0. So okay, so we conjoin for each node, we store the minimum cost. If we have some node and it has only one child, then the cost of for each node, we store the minimum cost. If we have some node and it has only one child, then the cost of that node is the cost of the child. If the node is a lead, then it's obviously cost 0. If the node has 2 children, the cost is sum of the cost plus the cost to join children. Join the children, iterate over stuff in the left subtree, find the best corresponding child in the right subtree. Iterate through the stuff in the left subtree and find the cost in the right subtree. That kind of makes sense. It kind of makes sense. So if I have like this subtree here, I iterate over all of like these values in the left subtree, and for all of these values I need to find some right value that matches the left value the most accurate. And this way I will join these two together. Okay, that kind of makes sense, but how to prove the complexity, right? Well, there are logarithm number of levels in the subtree. For each level, there are some. Yeah, I can see how to prove the complexity. I think so. Because of the logarithm number of levels in the subtree, for each of these levels, for each of these nodes, you will only iterate through the size of the node at most, right? So through the size of the node, and this size of the node is essentially nlog n in amortized things, and that's why it's nlog n log n. I mean, yeah, I think I understand what he's saying here. But that's an interesting solution that doesn't involve anything other than just a custom-made try. Very, very interesting. Should we code this? Let's see how many. Yeah, we went over the 2-hour mark. Maybe we should leave this to the next time we stream. But I want to code this. I want to code this specific solution. Just to prove, like, I'm kind of afraid of the time complexity, though. It's because kind of looks like a lot of iterations through dynamic memory. But because there are no addition, there are no subtraction of numbers, this should be faster than the editorial solution. Because they here add numbers and subtract numbers, this is slow. This is slow, but this should be very fast. This is just one DFS and one more DFS. So like 2 nested DFSs with, Okay, so I think I will leave this for the next time. Maybe we should like go and yeah, like now I think the stream is enough today. What happened with the camera though? What happened with the camera? I don't quite understand. So something, my camera, something. Let me just check it. Okay, I don't know what happened with the camera. I will take a look later. I don't know, but I will end now this stream here. I don't know what happened with this, but the next time I will certainly solve this G. And then maybe come up, tell you guys more lemmas here. So yeah, thank you guys so much for watching. I hope you had a wonderful time, and see you next time. Thank you, by the way.